The substitution methods is one of the most useful methods in integration. So there is a way for you to like memorize formulas on how to solve equations or how to integrate functions such as these, where you have a complex like linear combination. But it's much easier to look at the substitution method because you can use it for complex examples. The substitution method follows from the chain rule, and it kind of covers the same things, so the same similar idea, but the approach will look slightly different. So the idea is that you're going to first substitute. So you're going to pick the value that you're going to substitute. Usually it's quite obvious, and here I'm going to pick 3x plus 1. Then what I'm going to do is I'm going to find the derivative of du by dx, and you have to make sure that your notation matches. So you're going to derive du by dx, whatever your variable is, and that's going to give me 3. Now what we're going to do is something a bit unusual. We're going to treat this like a fraction when it's actually not. And what we want to do is we want to make dx the subject. So you want to cross multiply in here, do whatever you want, but making sure that you get dx to be the subject. So a way to do that would be, say this is over 1, cross multiply, this is the long method. This will give you du equals to 3 dx, and then you divide by 3, so du over 3 equals to dx. Again, this is a bit unconventional because du by dx is not actually a fraction, but we're treating them as such here. So that's one way to do it. So we'll end up with du over 3 is equal to dx. Another way to write this as well would be, for example, 1 over 3 du equals to dx. Maybe this notation is much better for you to use. But that's something, because this is 1 over 3. So just keep this in mind. So then I'm going to do 2 substitutions, actually. Instead of the 3x plus 1, I'm going to put my u. But because we substituted with u, we can't just leave the dx there, which is why we're doing this whole method. Because once you substitute u, there's no x in there. So if I tell you integrate by dx, you're going to tell me how. There's a u in there. There's no x. So we rearrange it such that instead of dx, we have an equivalent to dx, which is du over 3, or 1 over 3 du, up to you. So now we have this, and everything seems smooth. There's less variables to deal with. And I'm going to use one of the integral rules. I'm going to take out the 1 over 3. So I'm just going to take it out. That's why I said this might be a better notation to use. And then I know how to integrate this. This is going to give me u to the power of 4 over 4 and plus c. And then I'm going to simplify this. This is u to the power of 4 over 12 plus c, and that's it. That's your final answer. But you need to bring back your substitution. So it's 3x plus 1, to the power of 4 over 12. Okay, so we have those... we can use the substitution method to help us with more complex examples. Another example, let's say you have this now. I'm going to use u for 5x plus 2, and then du by dx is equal to 5, and then so du over 5 is equal to dx. So then I'm going to do the substitution. I'm going to substitute the u, and I'm going to replace the dx, and I'm going to get this. So I'm going to take the 1 over 5 out, and I'm going to move the u to the power of 4 from the denominator. I'm going to move it to the numerator by changing the power to a negative. And then I know how to integrate this. It's going to give me u to the power of negative 3 over a negative 3. Simplify this, and that's going to give me a negative u to the power of negative 3 over 15 plus c. I'm going to bring the u to the denominator just to make it a bit more convenient. And then I'm going to put back my value in there, so 5x plus 2. Making sure you don't forget the negative in here. And that's to the power of 3 plus c. Always derive these to see that you get back to the integral, to the integrand, and that's like the best technique you could use. It's always useful to check, and they're easy to check, especially for complex examples. Another example, so maybe pause and try this on your own if you want to. So the u could be the 4x plus 3. I'm going to derive it. It's going to give me 4. Also, you'll notice that most of the examples here are going to be linear expressions and not anything complex. So the more complex expressions will come later on in other videos. So du by dx, I'm going to rearrange it. I'm going to get du over 4 equals to dx. And then I'm going to do my substitution. It's going to now be e to the power of u, and then instead of dx, it's going to be du over 4. move the 1 over 4 to the end, and then you have e to the power of u, and then du. And I'm going to integrate it, and the integral of e to the power of u is just e to the power of u. And then we just put the substitution back, and that's what you get. Hopefully soon enough, you'll also notice some of the tricks, just like you should have noticed with the chain rule, that there are some tricks you could use where you don't even have to do the substitution, but it's very good to practice the substitution with really simple examples until you find your own shortcuts. And the better you are with simple examples, the easier it's going to be later on for more complex ones. Let's look at this one. If I substitute u equals to 3x plus 2, derivative is u, rearrange, and then substitute back in. I'm going to take the 1 over 3 out. Now, 1 over u, this is a u to the power of 1. It's not like this example where I had u to the power of 4. So just be careful in the denominator. I just have u to the power of 1 here, so the derivative is ln absolute value of u. So 1 over 3 ln u plus c. And then I'm going to put the substitution back in. Make sure your absolute values are there. That's going to be 1 over 3 ln 3x plus 2 plus c. So hopefully this was clear. The substitution method isn't that hard. It always follows the same thing. But just remember this step where you are rearranging the derivative or the derivative expression. Remember, du over dx is not a fraction, but we're doing this unconventional thing, and we're treating it like one here.